All right, we are officially recording here. Okay. So I don't want to say we have a lot of things to go through, but it's been a while since we met because we had exam last week. It looked like it went pretty well. I graded it. I think, a couple minor problems here and there, but they were all pretty good for the most part. The average was like 82 or something. So they were good. Couple hundreds. Couple other ones, other ones on the low side, I'll probably reach directly out to people and kind of connect them directly with Chima. Chima's been under the weather this week, so hopefully he'll be back soon in contact with everyone. But back in the swing of things. But I posted a couple of announcements last week. Everyone submitted it. This week we're going to be discussing inferential statistics. It's a big fancy word for how it compares to random. That's all it is. Because we were talking a little before, how do we compare what's the best or what's this or the highest or the lowest? We use descriptive statistics, and this first exam focused explicitly on descriptive statistics. Highest, lowest, z-scores, mode, mean, median, mode, all that other good stuff. This class or this set of classes is going to be on inferential, and then we're going to talk about correlation or correlative statistics. So inferential, how does it compare to random? What's random? When I say the word random, what's it mean? What's the word random? Without defining the word random. How do we define the word random? Not intentional. If I had like points just thrown up randomly, what would it look like? What's that? No uniform pattern. No pattern. No, the highs next to lows. That's what it would look like. If we're looking at today, we're going to talk explicitly about point pattern analysis. And so Michael, he's not here yet, but Michael collected a set of call box emergency points on campus. And what we're going to do is we're going to see if they're random, clustered, or dispersed, kind of on that type of continuum. Last week, I was at, a couple weeks ago, I was at the NC AUG meeting. So when we missed, that stands for ARC Users Group. These are people who use GIS in the state of North Carolina. And this was about 200 people. In mid-March, there's going to be the North Carolina GIS conference. It's every other year. We're going to have two students who are going to receive awards for undergraduate work and graduate work. I think we'll have a good idea who our grad rep is going to be. And so we're really kind of looking to provide opportunities for people. But those student awards, I think they win a scholarship, free registration, because student registration for a lot of these conferences is minimal. I cover it all. I typically cover it all. And it's just the pain dealing with campus and all that other stuff for me to pay it and all that other stuff. But that's a big one. That's about 1,000 people who practice GIS. ARC Users Group. There's about a couple hundred people who kind of do GIS work, manage a lot of the GIS in the state of North Carolina. I was talking to someone about NC Live. So nclive.org, and a lot of the data sets there. There's one called Social Explorer. There's one called Data Axle, which means the state of North Carolina has subscriptions to them. And so you could query out business data. So I can look for all the businesses that satisfy a certain NAICS code, North American Industry Classification Standard, or SIC code standard industry classification. So I can say, let me look for all the fast food restaurants, and I can map those. I can map all the vape shops or whatever I'm looking for in a particular county, and you can download that data into a table. Now, once you get it into a table with like the address or the latitude and longitude, can you turn that into a map? Of course we can. We can do something called geocoding, or we can do add XY. And with the group of PhD students that we've been working with, if I have an X, I've got a Y, I can make a map out of it, really easily. So he was talking about Data Axle and Social Explorer for census data. There's a lot of good data sources out there. Another thing that I always kind of push is 3-minute thesis competitions. Well, one of the reasons is because a lot of my grants, they want me to say, what are students doing? Because a lot of times, like students, I give you money and stuff, I need to report to NASA, I'm meeting with NASA next week. I met with them Monday, like, hey, how many students presented at 3-minute thesis? How many students presented at GERS? How many students how many students did you take to NCGIS? If I say, well, they didn't want to, I'm sorry, what do you think is going to happen? They're just, we're going to cut it, we're going to cut it, so be really careful and take advantage of some of these opportunities. And then, like I mentioned before, I've started grading assignments. And so, moving forward, anything that's late is going to be late. Like if I grade, I usually grade it like the day after. If it's not there, when I grade it, it's late, and it'll earn half credit. A lot of times people kind of ask me tangentially, like, can I still submit it? And I'm like, sure, go ahead. It's still going to be late, so a lot of times I expect people, when you get into the professional world, kind of really trying to be a little bit more direct about your questions. Hey, I'm going to turn this in late. Can I earn full credit for it? And don't be afraid to ask for that. And don't be afraid to me say, no, I'm sorry, or whatever. So to me, that's part of kind of really being a professional, kind of going from, student to, professional. So be aware of that. I don't want to talk about the story when we submitted this grant 3 minutes late, and we ended up getting it the next year for like $417,000, the same exact thing. We were submitted with Clemson and Fayetteville State, and someone misread the time, like the Pacific Standard versus when we submitted it and we appealed, and like, well, it was due at 5. I don't know what 5 means to you, because they thought it was 5 o'clock Pacific Standard Time, which would be 8 o'clock our time. And they looked at it as like, no, it's due at 5 Eastern Standard Time, and so we were arguing. So the next year I was like, forget y'all, I'm going to do it. And I'm going to get, $400,000, fund a bunch of students. And it was good to go from there. And so be aware of those things. Because when you submit, a job application or scholarship stuff, and it's a minute late, it might as well be 100 minutes late or 100 hours late, because it's still late. So, taking something half credit, that's probably a pretty, easy lesson to learn on this. Daniel had a question about position paper, right? You thought you missed it last week? You didn't. We're going to talk all about position paper here. Okay, so we got the position paper. Position paper. I got a rubric right here. 10% of your grade, and to me, the position paper, this is probably my favorite thing in this class, because I really want us to put to practice the skills. I offer readings and exams and assignments just because, I hated the classes where it was just based on 3 tests or, 1 paper or whatever. So, I threw in a lot of different assessment and evaluation techniques in case you were good at one or not good at the other or whatever, to counterbalance some of these. But I really like this position paper because I want this to serve as the basis for maybe your thesis or your dissertation or your project or something that can be submitted. Because in this position paper, it's not required of undergraduate students. So if you're an undergraduate student taking this for undergraduate credit, you do not need to do it. The undergraduate students who are signed up in the grad version of this class, you got to do it. You're signed up for 5130, you got to do it. No ifs, ands, or buts. And then I've got a few students who took this as an undergraduate and now are registered for the grad version. And they're like, do I have to take the class again? I was like, well, you got to do the paper, you got to do the paper. So, all the other assignments will apply. So I'll average your grade that you earned in the undergraduate portion with the paper. So if you don't turn the paper and you got an A, then it's probably definitely going down to a B or a C, depending upon what your grade was, since it accounts for 10% of your grade. So we'll be answering critical questions that we have. This is something that we can submit to something like North Carolina Geographer. North Carolina Geographer is a journal. I don't like the way it works, but people love journal articles, especially the people for my job and dissertations and all that other stuff. They love paper submissions, even though I don't really read that many of them. That's not my nighttime reading. But one of the things I want us to do is to reinforce, make hypothesis because we can open up our computers or open up these phones and we're just deluged with fact after fact after fact after fact. And I want us to be able to be equipped with the skills, the data skills and the statistical skills so that we can prove or disprove these. And it's okay if you don't disprove these. Things like cancer rates are concentrated in certain regions of the state. You know, concentrated cancer rates are higher around cities than in urban areas. You know, and we can, you know, what's the word around me? We talked about this before. Maybe within 15 miles or 20, I don't know. Those will be the things that you define. Drug-free crime zone policies are working because drug crimes in Durham are lower close to schools and regions further away. We got a GIS data layer from NC1 map of all schools. We can go get all the drug crimes from Durham Open Data. How many drug crimes are within schools? How many drug crimes are outside of schools? Okay, we probably want to calculate the rates. That's normalization stuff that we talked about at the block group level. So how are the rates within a certain distance of the school outside of other distance of the school? You know, by mail voting patterns are highest in rural regions. So what we try to do is just prove or disprove some of the data we have. This is the rubric. Those of you know me, I love rubrics. I love everything, you know, being quantitative, very quantitative in nature. But I want you to develop your own data as well. You can also develop your own data as well, integrate it into your master's thesis or project. It needs to be original, needs to kind of prove or answer a specific thesis or question, just a hypothesis. And a lot of those papers that I've posted down at the bottom of modules, you'll see like in my first couple paragraphs, I put in like bold and italicized, this is my working thesis. I might even have a couple of bullet points, other things that I'm trying to do so that people reading it know exactly what you were looking at. You know exactly what you're trying to prove or disprove. And then right at the end with my conclusions, I've got 2 or 3 bullet points right at the end. I found that this, I also found that this. And so that's the way that I do things. So if you don't do it, then you'll do just fine. But I try to be really direct. And a lot of times when you write a paper, it's like, I'm going to tell you what I'm going to do. This is what I did. And I'm going to tell you what I just did, you know, in the conclusion, just kind of reinvent it other ways. So it's 4 to 6 pages, single space, not including figures, charts, graphs, cover page, works cited, table of contents. So single space so that you can kind of make it double spaced and submit to somewhere. To me, this 4 to 6 pages is going to go by real quick once you start working on these things. I've done a lot of the research in some of my papers. Feel free to do it, you know, because someone went and did the research for my papers already in other papers, and I just went and added a couple things that are kind of contemporary from, you know, 2021, 2022, 2023. So you're not going to go and do just a brand new original introduction, you will. Why is this important? But you're not going to do a whole new lit review. You can't do that much in 4 to 6 pages. You know, the biggest challenge with papers is, you need me? Oh, okay. The biggest challenge when you write papers is making them shorter instead of making them longer. We submitted something, Dr. McGinn and I submitted something to the professional geographer, which is like the professional and applied arm of the Association of American Geographers. It had to be 3,000 words. Those 3,000 words go by real quick. You know, you got to pick and choose your words really, really, really well. And so I also in there, I put a template. So, and I also matched it up for had an interactive table of contents. So you just update the table of contents and it's got all the sections in there and it's got table of contents ready to go. So if you don't know how to do that, just use my little template. Okay, I know a lot of people here are probably better at Word than I am. So introduction, why is it important? What's your hypothesis? You know, why do I care about this? Okay. Other thing, lit review. What have you been doing? 5 different works. Make sure we use in-paper citations down here. Okay, I'm a big fan of in-paper citations because you're going to need to use those at some point in time. 1 paragraph lit review if you want. Methodology, what'd you use? Where'd you get the data? Results and conclusions. Did your conclusion adequately explain it? And it's okay if you don't. Dr. McGinn and I had a paper where the exact opposite was proven with statistical significance. Do you have any maps? Are they good? Grammar's important, really, really important. And then the project difficulty. You know, I've posted a project right here. So if you go to the position paper, I have a position paper MXD sitting here ready to go that you can utilize data. So if you're like, I don't know what I want to do, take some of the death data that we did. Hey, cancer rates, deaths at the zip code level, some of the stuff we already done occurs at higher rates in low income areas compared to high income areas or whatever. Remember, we did some age grading and all that other stuff. I think we focused on these 10 counties right here for some other things. So feel free to utilize these. But if I were to right mouse click and look at open attribute table, look at open attribute table right here, I got tons of things here. I've got COVID rates, average number of vehicles, total population. I got a median age, distance to the nearest supermarket. Is it metropolitan, micropolitan, percent minority? This is absentee balloting for 2020. Poverty rates, people below 2 times the poverty rate line. I think I have things like percent Democrat, percent Republican, zip code. Is it in a food desert? Yes or no? A USDA food desert. People who live in food deserts spend less on fruits and vegetables than people who don't live in food deserts. You know, that maybe reinforce something. We're going to look at something in a couple weeks or maybe next week called the two-tailed t-test. That's my go-to tool. That's my go-to. You know, I'm not a big correlation person because there's a lot of other variables there. Spatially, my go-to tool is GeoSort. You know, hotspots, spots, as long as I'm using normalized data or age-graded data, I'm good to go. So two-tailed t-test. So we're going to be talking about those tests a lot. You know, that's my go-to tool, even though there's probably 50 other different tools out there, you know, but we have mean, median, mode, standard, you know, we have all that stuff out there that exists as well, but kind of above and beyond those to prove some of these things with statistical significance. So I've got some data out there. If you were to look at fields, uncheck all those, you'd see tons and tons of other fields that I've collected there. But hey, I want to look at a relationship between percent minority and spending on fruits and vegetables, or Democrat or poverty or things like that. But there's tons of other things out there. There's a lot of other data sources out there, like from Social Explorer that we have access to. I was working with someone today on the vital statistics database. Cameron has tons of data on, link your deer vehicle crash data with this, median house. Somewhere there should be like median household income or poverty rate somewhere in here. Is there a relationship between motor vehicle collisions and poverty, or maybe population density or something like that? And to me, I try not to answer the why questions because I don't think I'm equipped to. I'm not a social worker, sociologist, or education major, but I'm more focused on the where. Hey, there are distinct spatial relationships between income and motor vehicle crashes. There's a distinct spatial relationship between how close you are, areas within 1 mile of the NCCU campus, and car break-ins. Why? Probably because there's lots of kids out there that probably leave their car unlocked. There's lots of younger people out there who probably want to cause trouble or whatever. But I'll kind of leave that why to the, people who answer those why questions a lot better than me. So here, what we really want to focus on is the where questions here. And if you want to talk about the why a little bit, you can. But I've had some students in theses. I can think of one about 6-7 years ago. They kind of went down some kind of rabbit holes right there, and and people across campus and public administration. We had some people from NC State that worked on committees and like, hey, let's just leave it, leave it right here. You're good, and stop with some of the other stuff. So I really like this project here because You got to think of a research question. What do you want to prove? What do you want to disprove? Daniel was starting to look at some climate data with hurricanes. Areas near this region have higher rates than this region or whatever. Okay. So a lot of these we've done some things with aerosols. So I'm really interested to see what we got, because the only limitations that we have are your imagination. And so please build upon this stuff. I've got stuff at the zip code level, but if you need stuff at the, county level, the tract level, the block group level, we can, to be honest with you, we can go and get it. If need be, watch this. We're at a point in time where you're logged into NCCU. I can go to this data right here. I swear I know what I'm doing. Portal, Living Atlas. And I can type in the word income. And I've got median household income. So I got median household income. And so when I look at these, I always want to look at the thing that says Esri demographics. But here's some median household income at different scales right here that I can go add. And then what I like to do is I like to go and is this just at the state level or the county level? Uh-oh, crashing my computer. Okay, it doesn't look like that. Okay, but I zoom in more and more here. Yeah, this area. And so we can see what areas these are in, and I can right mouse click. And you can see this is growth, annual growth. I can right mouse click data. I can't export these things, but there's other data sources out there that we can go and import, export, do whatever we want with those. What we're looking at here are just COVID rates or whatever. So, you can kind of work with those if you want there. Any questions about the position paper? I kind of look forward to it. I really enjoyed the position papers. This is a position paper that someone wrote on, let's see, what do we got here? Spatial analysis of COVID-19 variation between urban and rural counties. They just want to see what's an urban county, what's a rural county, and all they did was just calculate the number of cases, the deaths, death rates between the urban counties and the rural counties to see if there was a difference between those cases per thousand population. So they just went and saw if there's a difference between those. Really at the county level, real simple, really easy. Okay, using the tools that we've got. What's that? Yeah. Oh yeah. No, I like it. This was another really good one that I didn't even think of. So the student went and got death records for 2019, 2020, and they wanted to see if there was a difference in suicide rates. This is a student named V, but we went and calculated suicide rates, kind of explained. She normalized populations. I think she made a little map right here. I don't like that thing right there. It's okay, but we're going to kind of talk about this previously, but this was the suicide rate in 2019. This is the suicide rate in 2020. They ran a statistical test and they saw that it was statistically different, but not that statistically different. It went up, but it didn't go up high enough for us to say that it went up. It was statistically different, because if I were to take like 50 people's heights and another 50 people's heights, there's going to be a certain margin of error. So there was probably about 84% chance that they were different. But when we talk about levels of significance or statistical differences and margin of error, we look at 90%, 95, and 99%. So something like this isn't quite that way. And it's based on things like sample size and other things like that. And so I kind of liked, I like these. And then you can see what they did right here. They gave me a couple of just descriptive statistics here. at the county level. So for 2019, 2020, they give you the mean, median, the mode, standard deviation, all these other things. Kurtosis and skewness are the relationship of how that curve, that normal distribution curve looks like. So she kind of did some things above and beyond what we were looking at here, but really neat, there's kind of real neat papers that you can build on for something bigger and better. All right, any other questions about that? So today we are going to talk about inferential spatial statistics. So we're going to talk about something called quadrant analysis. I like quadrant analysis because you use GIS skills, you bring this stuff into Excel, and hopefully by the end of today, we'll kind of get into that. So I'll have my lecture here for about 45 minutes, and then we're going to start getting hands-on with exercise 5 because I want to kind of get through some of the quadrant analysis. I post a really robust tutorial on how to run quadrant analysis. It's like a 17-minute video. So if I don't get done with everything, and like I said before, we're going to be utilizing some of Michael's data that he created over the summer to look at spatial distribution of emergency call boxes on campus. And so I like that data set, and we brought it in here to look at the distribution of that as well. So you can see everything I've got here. I've got a reading 3 in which I run some quadrant analysis on bear sightings in New Jersey. So I kind of like that as well. But that won't be due for 2 weeks. So I'll kind of start talking about some of the things we've got, and then we'll take a break, and then we're going to hop into exercise number 5. So. All right, so we're going to include point patterns. And this is actually taken from a student who went and did her PhD at UNCG, where we're looking at a map in southeastern North Carolina of large supermarkets. And you can see the distribution and distribution of these sales volumes for large supermarkets. Here's some other maps right here. This is what we call the REFI, Modified Retail Food Environment Index. Now, actually, this is Rhode Island, but I was here like 4 weeks ago. So I was in little town Bristol where my grandmother lived, and I was born over here. But you can see it's a whole bunch of islands and all that other stuff. This takes like 45 minutes to drive through the whole state, so it's really small. It's like the size of Wake County, literally. So it's a relatively small state here. But this is their Retail Food Environment Index, which is the ratio of healthy food sources to unhealthy food sources here. And so this is kind of skewed a little bit because, some of these areas over here, there's really not anything super rural right here. But if you have one food source in it and it doesn't have, and it's healthy, then it has 100%. If it doesn't have if they have one food source and it's not a supermarket, it's 0. That's like the only 2 choices, like 0 or 1, or 0, 50 or 1, or 0, 33, 67 or 1. And so we deal with some data granularity issues, especially in rural areas with something like this. But we're looking at here. This is part of the paper that Dr. McGinn and I did, where we're looking at the percentage of mail-in ballots for the 2020 election. So percentage of ballots for the 2020 election. And so these areas that are darker, up between 13 and about 33% of the people mailed in their ballot. They didn't even show up at a polling place in September, October, November of 2020 during the 2020 general election. And so you can definitely see some clustering attached to those. And what we're going to be starting on differential statistics is things like this. We're going to make these hot spots and cold spot maps. So we're going to turn a map like this into a map like this, because who makes these classes and colors? I did. I could divvy them up however I wanted. I could do equal interval. I'm a big quantile person, so that each color appears the same number of times. I could do standard deviation or whatever. So I made these, so I can change the map or manipulate the map to kind of tell my own particular story, but things like this doesn't lie. But even with this can lie a little bit. In the group that we were talking about before class, we're talking about, all right, I ran an interpolation algorithm, but I changed the parameters around so that I only set up a certain search distance or cell size or power, like second order, third order, fourth order, so that the results might change slightly. So this is the percentage of mail-in ballots. And so these are clusters, hot spots, and cold spots. So these areas, these dark areas right here, are areas where people mail in their ballot at higher rates, surrounded by other people who mail in their ballots at higher rates. Okay, so just one zip code, it doesn't make it a hot spot. It's got to be high. Now, what's the definition of high mean? Was that above average? We know how to compute the average, right? You bet we do. Okay, to add them all up and divide. Now that average is going to be kind of goofy from time to time. When we did like African American female breast cancer rates, when we ran that, it was data, and there was a zip code that had 4 people, and one of them died of breast cancer, so it was like 25%. And what do you think that did to the average for all 700? Moved it up, and then tweaked all of these hot spots. So we're like, anything with a population of less than 100, we're going to have to get rid of, not only for the zeros, but also for those other high values, where that you happen to have 10 related people who lived in that zip code that all died of breast cancer, then you're going to run into some major issues. So I like these because these are high values surrounded by other high values. There are input and distance and location parameters that we're going to talk about on the last week of class that we can tweak these with a bit, but these are high surrounded by highs, low surrounded by low, and this says, 90, 95, there should be a 99 there, but 90, 95, 99% confidence level. And so in theory, like 80% of these should be yellow, and then the other, we got 10% blue, the other 10% blue. So some of the things that I start to do with my two-tailed t-tests and things like that, like, hey, let me look at all these red areas. Let's look at income. Let's look at race. Let's look at Democrat, Republican, all that other stuff versus the blues, because they're literally on opposite ends of the spectrum. Are the incomes in these red areas different than the incomes in these blue areas? Maybe. There's a distinct possibility. This is a COVID-19 rate. You can see this cluster of COVID-19 going right around Fort Liberty right here, right? That's kind of interesting because no one in really Fort Liberty had COVID because they were kind of locked down a little bit more than this corridor along 95 that made this U shape. And this U shape actually moved from here, made its way to here, which I thought was interesting. What's that? Is that near this one here is probably along 95. And I don't think COVID's traveling because of highways, but I don't know why. But over here, I don't know why. But some of the measures that we can look at, and we talk about these inferential statistics, when we map density, like number of stores per unit area, I look at the kind of the proliferation of grocery stores versus farmers markets. There's much less farmers markets than grocery stores than fast food. So I can't compare density because, well, there's obviously going to be different densities, number of grocery stores per 1,000 people or whatever. Other things like RFEI, Retail Food Environment Index, we've got a lot of zero values. The Modified Retail Food Environment Index, rural areas have a lot of zero areas. RFEI is another thing called the Retail Food Environment Index, which is the ratio of fast food and convenience stores to grocery markets within a enumeration unit. Other things, the average distance to the nearest food source, we see things like that, where that values are expressed in absolute terms. Travel methods measures are not specific. So our most recent paper, I don't think we might have posted it in there, where that, there's like 8, 9, 10 different ways that we can just measure availability. How close is healthy food, Dollar Generals to us, or at this block group level or zip code level? I could just count the total number within it, but well, there's probably going to be more Dollar Generals or supermarkets in more populous zip codes than others. So that's not really a measure of true relative availability. And so people have metrics like the number of dollar stores per square mile for this, but the calculations are a little bit more robust. And more robust calculations leave more chance for error. And then COVID-19 rates grouped by the zip code level. So as we said before, I make the maps. So I decide how the maps appear. But geostatistics, they're going to pick those up. So when we look at spatial patterns, we've got what we're going to look at first, and then later we'll look at clusters. We've got our global statistics and our local statistics. So when we look at patterns, I've got a set of points, and then how clustered is this entire set? How dispersed is it, or how uniform is it? Or random is another word here. And then we've got clusters, which are local calculations where at my zip code versus your zip code. Are you in a blue? Are you in a yellow? You're probably going to be in a yellow, because a lot of times when we look at random data, in theory, the whole thing is going to be yellow because you got highs surrounded by lows and middles and not highs or whatever. We'll talk more about the actual calculations later. I don't want to do a whole bunch of math here. I want us to be able to interpret these things as well. So once again, we've got global calculations. Today, we're going to focus explicitly on the global calculations. Next week, we'll talk about the calculations, because when we look at spatial autocorrelation, there's a lot of different ways to define it. It's the confirmation of Tobler's first law that we talked about in the first week, where that like things, more related things are closer to things that are more related to themselves than anything else. We can use similarity, we can use probability, and we're going to use correlation. And what we're going to look at right here is probability, the extent to which occurrences or an event in one geographic area makes more probable or less probable the occurrence in a neighboring geographic area. So we're really going to focus on probability. So when I look at a set of grocery stores, how does it compare to a bunch of random points? Because some of the random points will be close, some of the random points will be far. And some of these like measures are really easy to calculate. You know, one's called nearest neighbor analysis. Like when you look at this, what is your nearest neighbor? How close are you to the nearest neighbor? Literally. And then you just do that for every single point that we're looking at right here. Yeah. So, and then we're also going to focus on correlation. How do these correlate with each other? So, Tobler's first law, everything is related to everything else, but near things are more related than distant things. So when you drive around a neighborhood, you know, the homes look the same, the income's probably going to be the same. And then when we look at different incomes or crime rates or whatever kind of we see with environmental indicators, environmental or social indicators, we can see they're more related to other things. So everything related to everything else, but near things are more related than distant things. So like I said, in this class, we're in the where business. That's all we are. Where, distance, close. Okay, how close are we? You know, urban and rural, well, we can figure out urban and rural, maybe based on distance, I don't know what. And so we can look at something called spatial autocorrelation. Okay, that's just a big fancy way of saying, are high values surrounded by high values and low values surrounded by low values? Yes or no? That's all it means. Here we're looking at a map of Puerto Rico. You know, so we're going to talk about this, interpret this in a little bit. Here's negative autocorrelation. So this is population density. So you can say high population density, low population density here. Okay, so high and low, and we've got some kind of middles over here. Here is competition for space. I don't know what that is, but this is negative spatial autocorrelation. But what I want to talk about with this today is inferential statistics. Okay, how does it compare to a random sample or randomized experiment? Okay, we infer. What's that word infer mean? Like you make a deduction based comparing it to something else, something like that. Okay, so we assume the data comes from a random sample. So when we look at these grocery stores, we're going to assume it's random and try to prove or disprove that it's not random. And so we can make these kind of, we're going to talk about null and alternative hypotheses next week. But as with these, the statistics have to have a relatively large number of cases. You can't have 3 points and figure out how random or dispersed they are. You can do it mathematically, but you're not going to get a lot of results. It's like saying just Michael, Cameron, and Andy, you're going to represent NCCU based on your height. So whatever your height is, we're going to say that's the average height of all NCCU campus. What would that mean? Like, well, they might be really short or really tall. They're really not a good representation of campus because, well, we got 8,000 people on campus. Now, would it make sense to go and measure the height of every single person on campus? It'd take a really long time. So we need to have an adequate sample size. And we're dealing with all this kind of political, I don't want to use the word nonsense, but political stuff right now. And so you'll see like 40% plus or minus 3%. That plus or minus 3% is based on the sample size because they can't go and ask every single person out there, every single voting age person, who they're going to vote for. We have confidence intervals, and this is kind of what I led to here was that we're 68% confident that the mean of the population falls between 1 and -1 or positive and -1 standard deviation of a sample mean, assuming that we've got a nice normal distribution. A lot of times we might look with logistic data, like do we want Trump or Harris or none of the above or whatever, when we're looking at categorical data. So we have these confidence intervals that we talk about. So this is 40% plus or minus whatever. And so a lot of times when we look at census data, it's difficult to get exact census data. So when we looked at that percent minority, median household income, poverty rates, it comes with a margin of error. I don't put the margin of error in there because it's just extra columns for us to interpret. But I wrote a paper, me and Dr. McGinn wrote a paper a few years ago where they said like, hey, you got to put the margins of error in there. Like, oh, crud, because certain types of data are going to have larger margin of error because there has a lower sample size. So things like education attainment, all right, they don't ask as many people education attainment questions as they do age and income. So if I say the median household income in this, block group here is $42,000 plus or minus $2,000, where that I might have something that says, all right, the percentage of people here that have a high school education is 82% plus or minus 20%. Well, it could be 102% or down to 62%, which is it's just a high range. And to be honest with you, not very reliable. To me, and some of the cautions, there's no correct method of inference from data haphazardly collected with bias of unknown size. And so a lot of times when we start thinking about bias and questions, and one thing in our university, we have students who take social work classes, and social work makes them go and create a form. Maybe back in the day, it was a paper form, but now we can create Qualtrics forms. We can go and create tons and tons of surveys. Like we have something here called Survey 123. I'm working with something right now called Quick Capture, which is even a quicker, way to capture data. So, hey, I'm polling someone. Who do you want to vote for? Boom, boom, and you can actually collect their actual location where you are. Who do you want to vote for? And go to the next person. You can walk around the city and get a, big map of different people. Now, what I did was I connected it to my GPS unit using Bluetooth. I started kind of walking around, and then I'm actually going to compare it to the actual phone, it's GPS unit, and maybe compare it to my little this thing, my little GPS unit that I carry around my wrist. But a lot of times be careful for bias because, imagine we went up to here, we were taking a poll and I'm taking my poll and we can have biased polls. You must really hate Trump, don't you? Yes or no? Oh, sure, yeah. They said yes, or whatever. And so be careful about some of the biases that exist with these. And we all have our own personal biases when we ask questions or work with data. a lot of times with that position paper, I want us to get out of the habit of trying to kind of reinforce or prove our, prove our hypothesis. It's okay if the hypothesis doesn't work, because you know what? If I say, urban, hey, if I make urban 30 miles from a city, it's going to prove my hypothesis. Then if I say urban's 10 miles, we go with the 30 miles, even though 30 miles, that's a pretty big margin. That's a pretty big buffer for urban. And so the mean is strongly influenced by a few extreme observations. Outliers can have a major impact on confidence intervals. And like I said before, when we did that research paper with a PhD student, when we did that research with the PhD student, we got rid of a bunch of extreme values for cancer rates. Okay there?
Please flip in that direction.
Oh. And so we can look at raw rates, because a lot of times when we think about data, we're looking at this normal distribution. And a lot of times when I do a two-tailed t-test, basically I have two of these line up on each other, and where do these median lines line up? If they line up on top of each other, we can say, hey, these data are the same. If we move far enough away here, we can say this distribution of data is different than this distribution of data. Now, how do we express or rationalize this distribution of data? Because right here we have confidence intervals that align with z-scores. Who knows how to calculate z-scores? You know how to calculate z-scores, right? You do too. You point to the people here. Okay. We all do, right? And so now we've got these z-scores, because most of the z-scores that you calculate, especially for normalized data, are going to be somewhere between like -1 and 1. You're not going to have -5s. You're not going to have +5s. Very, very rare. Most of them are going to range from like -3 to about +3. And so when we start calculating z-scores, because that's all this inferential and hotspot analysis does, is converts our z-scores, and with Geostats, it creates something called a GI score to a z-score to a nice pretty confidence level. And it says, hey, if you are 1 or 0.05 or 0.01, we're going to make you red or pink or dark or red or pink or red or dark red. If you are 0.1 below the mean, 0.1 below the mean, we're going to make you light blue, medium blue, dark blue. So that's all we do here. So when we see that 90% confidence interval, all it means is that z-score is plus or minus 1.65, based on whatever we're looking at. Now with hotspot analysis, that's what we look at there. So a lot of times we can kind of look at something like this. So when we saw that hotspot map, right here, we saw a lot of yellows. Why? Because most of them are between the 0.1 on one direction to 0.1 in the other direction. And we just know that anything that's a cold spot or not significant is going to be below the mean versus above the mean. And so we can look at normal distribution right here, because most data is going to look like this. Because we talked about in one of our lessons, I think week 2 or week 3, was it's important that we normalize data. That's important. We work with normalized data, because we got population, that's not really normalized, okay? We want to work with normalized population density is going to be more normalized. Because what we're going to work with today, we're specifically looking at point pattern phenomena. Next week, we're going to work with polygon phenomena. We've got a polygon, we got a county, it's got this cancer rate, it's got this median age, it's got this whatever with polygons. Today, we're going to work with points. Let me just look at a bunch of points on a map and see if they're clustered, dispersed, or random. Why do we care? Who cares about the arrangement of points? Fire stations. Fire stations is a perfect example. You want them to be dispersed as possible. We want fire, we got somebody, you still work for the fire department? Volunteer fire department. So like you see, you're driving along on a rural road and you see this like random fire station, like what's this doing here? Because they need to be deliberately dispersed. Okay. What are things that should be close together? What are things that should be close together? Gas stations. Yeah, and gas stations are close together, but a lot because of the zoning attached to it. You just can't see gas stations in random places because it's because of the zoning attached to those. But developments and people and cities, you don't have some specialized doctor out in the middle of nowhere because they want to be where the people are and vice versa with those adequate services. Okay, and then like supermarkets. Hey, most of the supermarkets around each other when we look at a multi-county scale. So we've got quadrant analysis. We're going to look at something called nearest neighbor. I'll mention something called K function. We don't look too much at that, but we're going to look at quadrant analysis. I like this. We're going to look at nearest neighbor index. And basically, what does it do? Calculates the average distance between features. So I got 1,000 points. How far is one point to the nearest neighbor? We go to point 2. Measure how far it is to its nearest neighbor. We go to the next point. How far is it to the nearest point? Then just average them up. And then let me just create a random set of points that we do this for. Those two averages compared to each other. Real simple. This one uses some GIS. I like quadrant analysis. I wrote a paper for it, so that's why I love it. But I wrote a paper for it, and we'll talk about the paper. We'll talk about the paper here, but we run the conglomerate Smirnov test. I like that one. And I like quadrant analysis because the units that we use are squares. What's the good thing about using squares? They're all the same size. I don't know how many people live within those because when I do normalize, we've got counties and zip codes and tracts and all that other stuff that take on these odd shapes and sizes. Now, the first thing we have is quadrant analysis. I got formulas here. Now, don't worry about this one because guess what? Excel does this for us already. So, and we're going to talk about this as well, where that I see a whole bunch of points on a map, and I want to look at how this distribution of points compares to random. And we're going to talk mainly about quadrant analysis. I might even kind of blow off the K function because I don't really use it. Just don't use it. So quadrant analysis is that we superimpose a grid on top of something, and then we just count the number of points within the grid and then graph the frequency. And then I throw it into a random distribution using a Poisson distribution. Yuck. Using this. I calculate this. I know what this is. What is this? What number is E? Anyone know what E is? Isn't that Euler's number, 2.718, something like that? I'm looking at Andy here, Daniel. Does this stuff ring a bell? No, this key. Michael, Cameron. Isn't this Euler's constant? Sure, yeah, that sounds good. But raised to negative this power, what's this little thing mean? Factorial. So who wants to do this? Not me. Who wants Excel to do it for you? Excel's going to do it for us. Okay, but we just need to make sure it makes sense. Just like when you calculate the weighted mean, the weighted average, all those other things. Hey, if I have numbers between 30,000 and 46,000, the weighted average better be between 30,000 and 46,000. So make sure some of these things make sense like we have for the exam. And I like that people kind of said, hey, the number I'm getting is not making sense. And I'm like, yeah, it's not making sense. You're right. They're not just putting things there for the sake of putting things there. So we're going to look at this don't worry about this because we're going to just use the function here. Because what we're looking at here in quadrant analysis here is we're going to look at the frequency of points versus a random distribution right here. And all we're going to do is just superimpose a grid. Now, we can make something called a fishnet. Okay, fishnet or a grid is just going to be like 15 by 15. And we'll talk about some of these with quadrant analysis where that I want to superimpose, because with these points, all I want to do is just count the number of times each of these points occurs in these. And I had this little function right here. L equals the square root of 2 times A over N. And so a county area might be 200 square miles divided by the number of points. If my units, I take the square root of my units, miles squared, I take the square root of that, I'm going to have something length in miles. Okay, and we're going to walk through this when we're done. And so when I create my fishnet, what do I want to do? I want to go and create a fishnet so that we have enough sample points, but we don't have enough 0 points. So I can create something just like this so that they're large enough to contain at least 1 point, but small enough to contain, 2, 3, 4, 5, where that, I'm only working with 9 points right here. So we might have too many 0 points, too big. It's okay, because a lot of times when we do our normalization these days, what do? We do it based on counties, census tracts, zip codes. Now we have the power to figure out what units we're going to create for this. So this is what we call a fishnet. Okay, fishnet. And like I said before, I've got a video on how to do this, but I want to kind of start on this video because it utilizes all the existing GIS processes that we've already done. So I had a student work on unhealthy food stores where they created like different quadrants, different quadrant sizes based on the number of points and the size of the quadrant area, and then so forth. We can calculate that, I think that's theta right there, but the average number of sightings per cell. It's kind of like, soccer, soccer, like you can calculate, what is the average number of goals per game. You get a really good prediction. What are the chances you're going to have 5 goals? Probably like 2% versus 0, 20%, 2 goals, 3 goals. And so our Poisson distribution looks to see if there's a difference between the known frequency and an assumed random frequency. So I'm going to create a curve. It might not necessarily be normalized. The thing about a Poisson distribution is that it might not be normal, but it's going to go up and it's going to go down, but it's not going to go exactly like a bell curve. And so this is one of the examples that we did where that we went and looked at farmers markets, the spatial distribution of farmers markets in southeastern North Carolina. Here are my grids right here. And all I did was I counted the number of times a point occurred in each of these grids. How do I count the number of times something appears in a grid? So I went to use the fishnet to create this grid. How do I count the number of times something appears in a point? We did this very first week of class. Some of you are like, holy crap, this GIS.
You do select by?
Select by a little bit more. Make it a little bit more permanent. Spatial join, exactly. We run a spatial join. So we run a nice little spatial join. Square. Okay. We run a nice little.
All right, that's a spatial join between the markets and the like counties. Is that right?
No, the markets. The markets and the quadrants that we created. And we're going to create these using fishnet, And Greg, he's online there, made a good point where that I only selected out the fishnets that were within my study area. So anything that kind of went outside, I didn't include because I don't have the areas outside, and I'm focused specifically on the study area. And so what I did was I ran a join and then I ran a summarize so I could see 8 of them had 0 points, 9 of them had 1 point, 7 of them had 2 points, 5 had 3, 2 had 4, 0 had 5, 1 had 6. And I use this Poisson distribution to figure out what are the chances that I get that. So I got an expected, and all I had was just a nice little graph right here that said, this is what I expect using, this is done all in Excel. This is done all in Excel right there. And so I just went and graphed it. So I graphed these versus the observed, and I get a nice little graph. So when I look at farmers markets throughout North Carolina, or this area right here, it distributes a random distribution, largely random. I run that conglomerate, whatever that test is, that conglomerate smear-off test that measures the area between these two graphs to see if it's statistically significant enough to be different. But these, the blue is what we see. The red is what we expect. How much of a difference is there? This is just random. And this was all done in Excel. I ran it into GIS and I cut and pasted it into Excel. This is convenience stores. Did the same thing. These quadrants are smaller because my sample size is higher. And now look what I get here. This is what I expect. This is what I observe. These are much, much different. You got a whole lot of 0 points. We don't expect a whole lot of 0 points. We expect, the most we expect about 61, 62, we expect them to have 1 or 2, while that here we have a whole lot of 0 points. Now, after the break, we're going to go through and I want to run quadrant analysis with everyone. I want to run these, at least I want to get one of the counties going, because I love the quadrant analysis, because we'll talk about the paper when we're done with the break as well. The other thing we've got, nearest neighbor analysis. This is, simple isn't the right word, but for all these points, all it does is that for point number 1, all it says is, hey, I'm going to go to all 1,000 points, all 50 points. How far is it from you to the next one? How far is it from you to the closest? How far is it from you to the closest? How far is it you from the closest? And so the minimum distances are added, and then we produce an average minimum distance. So it averages up all the minimum distances, and then it uses a square root of the area of the region divided by the total number of points. Does that ring the bell? That's what we calculated before. It's applied differently. And so we calculate potential random distance, and all it does is just compare this random distance to what it would be for a true random distance to figure out how different they are. Okay, and it runs it into an index. So if the index is equal to 1, the data are random. If they're less than 1, it shows evidence of clustering. If it's greater than 1, there's a uniformity, kind of like with cell towers. And so typically our continuum goes from dispersed to random cluster. Because when I do this calculation, these are going to be really close to each other, except for this one. For this one, all the points are going to be really far. Now, for the clustered one, somewhere in the middle, some are far, some are close. So with the clustering and the dispersion, there's intentionality with the arrangement of points. Where that random, they aren't. All right, let's do some math. Okay. Now, this is the math that we basically look at right here. It's the observed versus the expected. The expected we throw into a formula. The observed is just going through and doing all the calculations. Now, this does this using the Euclidean distance. What's Euclidean distance mean? Straight line. We know how to calculate Euclidean distance, especially on a plane, using the distance formula. So that's why I personally like working with things like state plane as opposed to geographic coordinates, because geographic gets wonky with your sines and cosines, your tangents, and all that other ugly stuff. Okay, it's also sensitive to area, so when we calculate the expected distance, it's 0.5 divided by the square root of n over a, the number of points over the total study area. So it is sensitive to a. And then we can, if we create, when we create that z-score, it's just the observed minus the expected over the standard area using this formula here. I don't want us to do anything like this, because what we're going to do is we're going to run a nearest neighbor index on convenience stores, and it's going to say, hey, the z-score is negative 24.167223. In the exam, did you get any z-scores of negative 24? No. What's that mean? It's a very big likelihood that this is clustered. Very major likelihood. Okay, and so when we run this tool, nearest neighbor, we get these nice, pretty, nice, pretty graphs that tell us exactly what it means. Here's another one that I ran. It said the observed mean distance is 46, 42. The expected is a little bit less, which is kind of interesting. The z-score is 1.61. Our p-value is just over the threshold for us to say that it's, or just beyond the threshold, or not as much the threshold for us to say that if we're looking at nearest neighbor analysis greater than 1, that means it's going to be more dispersed as opposed to clustered. So it's close to clustered, but not quite with that 0.1. And so we can see here, the pattern does not appear to be significantly different than random. So we have these nice kind of wizards. So my big thing is I want us to be able to, kind of interpret these numbers right here. There's another one here called K function. I don't use it, but it looks at different bands. Let's forget about it for now. And so what we're going to do, how about we take 10-minute break? We'll come back here at about 6:20, and we're going to focus on, we're going to open up exercise 5 and start working on it. We'll talk about the paper that I did, but it's not due for 2 weeks. But I want us to do quadrant analysis, and we'll do a little bit of the nearest neighbor. We'll probably maybe just do one county for the nearest neighbor. Then I want us to get into quadrant analysis, because I've written whole papers on quadrant analysis and just some of the good things about it that go above and beyond statistics. It gets into some of the raster data that we were talking about before. And hopefully everyone's going to be taking raster GIS class next semester, right? Raster GIS, good. Maybe data science too. Good. You guys, Andy will probably teach me data science, and Daniel too. You probably teach me data science. You guys, he does a little programming in it. Did you take, you took it last semester, right? Okay, Daniel will teach me something. No, but we're going to do some Python stuff, my Python stuff, but we'll also do some other kind of open data, things like that. And it's good for people who don't have any programming experience at all. So let's take about 10 minutes here. We'll start up here at 6:20. And let's cheer for the Mets too. We got to check out. Oh, I'm a Mets fan. Yeah. Oh yeah. We're going to tune on the game here for a little bit. One of my friends is going to the game.
Oh, yeah. I think that's wrong. But no. She doesn't know, she hadn't gone back to her either.
Come on.
Yeah, it's close. Yeah. Maybe it's locked in, I think.
Oh.
Although that's what we never took, it was a front to. Yes. Yeah. Oh, okay, I mean, that's just. No, no, that's the. Travel. Is she up on the rest of the day? She picked up in 5 minutes.
She said.
Yeah, yeah, regular. She's still. How expensive. See what's doing for that. To the bill. To the. For your stereo.
Oh.
Ways to get it. Can't even go back. I tried to go back. That's what I was telling the rest of them today. Everything is a picture. Grabbing the Google.
I thought she was still what she did in the first time.
And then she expected, that's what I thought, and she's distracted.
Sorry, I didn't do it.
So it's like, he doesn't.
Some serious something. Yeah, no.
Yeah.
Those are supposed to be your teams. Yeah. I'm still trying to just that's a good way of finding the shot. But we know where it's all you need to do just change the direction. That's session. And the focus on that.
I was thinking someone, expert in this field, geostats. Expert. She picks her.
He's going to check out. You give him access to something with expert.
I'm trying to figure out a way for it to be beneficial to you as well. When you teach, you also learn it better. So
You can force it. You really force it to learn and teach out. And so they can even take some time to second time. Time maybe the second time. That was just right?
basically, yeah.
Second time.
I'll make time.
What's the next thing was best for you?
Yeah. Then actually the next time I'll be able to start is like after the 18th. So not this Friday or the next, but the third.
I think I don't know.
Yeah.
So the TA,
Setting up. I'll talk to you. Let's see how. Yeah, I'll say. I don't hear. You can't say. She may. I need the medical station door. I got you. Sorry.
I'm
Say that.
okay.
Organize.
can do,
Making sure that everybody.
I gotta get on this.
we can start, I can bring out one picture.
My wife, I had to do a nap and then I get back up.
I'm somebody just jazz. She would like,
But
stop.
yeah, I just wanted to first thing like, you know, about this big project.
Just.
Yeah, it's very similar, it's ribbon, job, all that, it's very, all those traditions, very similar. So I'm getting it. It was like, visual noise and that little joint. I know we want to work together. Yeah.
Monday.
Gonna be.
Have to be there, so you get a better over the different. With that one or others.
Actually, Monday, it's
All.
Tuesday, my music last on Wednesday, I have class. So, and then the weekend. Great.
Typically, the virus, street life, share all concerned opportunities.
And I work until five.
I,
I work until five every day. I'm off on Friday, this Friday, my first. And then I'm about to work outside the evening and then practically something. So,
so one was.
this Friday, I have my dinner. And the day after my dentist appointment, and before I. So we'll start like
What about?
4:30. So I'll have all these. Yeah. Also, I have my son's deposit in the morning. That's great sign. So. Okay. Running the rest. So, yeah, I just need to. Until I. And I see around to the box.
Oh.
Yeah, how to go work that. But I need to work out. Had it one day, I got this. First of all, it's very But I think one of those important things is that, you know, it's because you have to travel, you know, you can bring these two tables together, then you can extend that. Yeah, so your information you get. Yeah. And then. Just need to-
Because, okay, yeah, I just sent an email to the Trump County Emergency Services.
Okay.
Because I haven't seen like throughout my entire journey, like, because I was born and raised here. And then I went to the village for like 10 years and then, so I haven't seen any type of direct driver. Emergency services. I know it's kind of done like in-house.
Okay. We've got about a minute here and we'll get started. Thanks for all of you for watching the baseball game online.
Here's some. also the more. It's something that's pretty important for. We're going to exercise. It's just a general.
It's the thing, I feel like citizens need to know how to react in a situation, because they're the ones that's been, they're like panic and forget how to be, and like just so crazy, and it's like.
Information will be go out to find some of things. You want to let them, probably, everything. Forecast the thing. Then, only did. It's not just part of it's fine. Like,
So fun, because when I go, this military practice.
Children in school are exposed to responding fire, check your smoke worker. Now, would it be more than? Well, yeah, they try to keep. They not as much.
Okay. All right, we can continue this when we're done here. All right, because I want to get home. I want to listen to the game. No offense. All right. So we're going to focus on exercise number 5. You can see for reading number 3, it's not due for 2 weeks. This is a paper that I wrote. It's using quadrant analysis and clustering techniques to quantify patterns of bear sightings in Northwest New Jersey. I grew up in Northwest New Jersey. I liked it. My brother was a master's student at UNCG. He passed away, and his wife gave me like a bunch of his stuff, and he had started this kind of work as part of his master's. And I'm like, let me go through and finish it. And so I turned this into this paper because some of the interesting things were when you look at bear sightings, and these are kind of category 1, category 2, which are nuisance bears and bears that are threats to people or perceived threats to people. It's just a random bunch of points here. And they previously had bear sighting maps, and I maybe showed this previously in class, but they're grouped by townships. Townships are like subdivisions of counties. Some are really big, some are really small. So you see kind of this checkerboard pattern because, the chances of a bear appearing in a really big county are much higher than a bear appearing in a really small county. And so to circumvent those issues, I want to make equally sized and equally spaced units, so the chances of having a bear sighting in each county are the same. And then in addition, we don't even need to calculate density. Why don't we calculate density if they're all equally sized? They're all equally sized. Why don't we need to calculate density? Because they're all equally sized, right? If we do number of sightings divided by area, if the area is the same, then forget about it. They're all the same. So we could just say 22 sightings, 13 sightings, 27 sightings, whatever, and make those pretty maps throughout. And so what I did was, we got a formula that we're going to look at here. We're just going to do this in Excel. That's all we're going to do. And then what did I do? I just created equally sized units. Look what I did. I just calculated the total number. And I did something called like density analysis, where I created a surface, a density surface like we talked about, and kind of grouped it by this way. Just so instead of going from like blue to yellow, we went from brown to middle brown to yellow. Because a lot of times when we see data, Tobler's first law of geography, and a lot of your geospatial statistics out there, they don't like seeing going from blue to yellow. They don't like that. Why? Because we go from high to low, and there's something happening there that we don't like, or something, or whatever. So this kind of just creates a little bit more of a continuous surface while showing the same general type of data. We're kind of just obfuscating the data a little bit, kind of smushing it a little bit, so to say. And so now I created this bear sighting map and some cluster analysis here. So you can see where bear sightings are higher. and lower. Yeah, actually, they had a kind of a bear sighting up here, a bear attack up there, up in Passaic County here. So I thought this was kind of interesting, and I ran some cluster analysis on all this good stuff here. But, one of the reasons why I ran it was because because you're not going to group bear sightings by county, by state, like we do a lot of things like deaths and motor vehicle accidents and things like that. So these are more like natural phenomena or environmental phenomena that will not be constrained by human-defined anthropogenic units like counties and block and zip codes and all those other things by which we measure data. So what we got here, and hopefully everyone opened up exercise 5 while we were all talking here, and we got a couple of different things going on here. So if you look at this project right here, we're working with kind of data that we saw a couple of weeks ago, and data we saw a couple of weeks ago with the deer vehicle sightings, and I think for next year we're gonna make sure I'm gonna kind of tweak this data a little bit differently. And then if I right mouse click on NCCU call boxes, I can zoom to layer, and then these are all the NCCU call boxes on campus. So this was the data that Michael collected last year that I kind of want to integrate. Hey, these are the call boxes on campus. Should they be clustered? Should they be random? Should they be dispersed? What should they be? They should be dispersed, right? Are they dispersed, Michael? I don't know. How about, let's do the calculation to see if they're dispersed. And that's what part of the homework is going to be, is that you're going to use nearest neighbor analysis just on this set of points to figure out if they're clustered, random, or dispersed. Because in theory, they better be dispersed so that everyone can have access to. And Michael, did you use Survey 123 to collect these? Yeah, and Michael used Survey 123, which is just an app that we put on the phone. I always like to create my surveys on my computer, and then I just go out in the field and just collect them. And he probably gave them names. They probably had names on the boxes, and I think he might even have an ID. And this is the information that Michael collected in our field mapping class last semester. So you can see, you can see Michael's name here. This is what we calculated. The date we collected, emergency, Lawson Street, where was it? And he collected some really good information. Is the street visibility, the night visibility, partially compliant? I assume this is probably some type of something for national safety. Yeah, so look at all the information he collected about it. Do you think he typed all that stuff in? No, you didn't type it in, right? Didn't you use drop-down boxes and stuff? I used them. Yes. Yeah, exactly. He used some drop-down boxes, so we went to each one, collected information about it, add some drop-down boxes, so you can go and do that, whether you're doing surveys of people or whatever. And these are all geo-referenced because very first thing you can do is map. So you can just say, click on a map and hey, here I am, and it's going to automatically collect your lat and long. And then we have other things with our GPS unit that'll get it. This might be off by 10, 15, 20 feet or whatever. Our GPS unit's going to get it within half a meter or so. And then you can get survey grade where you're getting it down to a couple centimeters there, But I'm not a surveyor and I don't claim to be one. So let's start. I just want to start working on this. I want to kind of get through some of these answers right here. Open up exercise 5. We're going to look at the distribution of deer vehicle collisions in Caswell County versus Rockingham County. First thing you'll need to do is extract the points. Okay, let's extract the points first. Where's Caswell County? Where's Rockingham County? Uh-oh, did I already extract these? Nope, I didn't. Okay. Because every year I do like a different set of counties. So, so I can see the Caswell counties versus what I have, Caswell, and I had another set of counties there. Yeah.
If you check the databases there.
Oh, thank you for giving away all the answers, one. That's okay. No, I do there. No, I'm just kidding here. But one said if you go to view and then catalog pane. And you go to databases. I've got actually everything that I've extracted out already. So I've got the Caswell deer vehicle collisions. I've got the Rockingham deer vehicle collisions. So I can kind of zoom over to these and zoom in a layer. So just for the heck of it right here, I've got the Rockingham and then I got the Caswell. And I can make these different colors. Now, just for the heck of it, what if I wanted to extract these out all by myself? Okay, so on the left are Rockingham, on the right are Caswell. I want to see which ones are more clustered, less clustered, whatever. So I got these points sitting right here. So those of you joining us along later, you don't have to go and extract these out all by yourself. You don't have to do a select by location, right mouse click, export to do it because Uncle Tim gave them to everyone there. Now, when we calculate the actual density, there's a lot more here than there are here. So saying like density is kind of, it answers one of these no doubt questions. Yeah, you can just drop it right. See the Rockingham.
So we just take it from that list and pull it over to the content?
Yeah, just take it from the list and pull it over because I don't want to sit here and waste all of our time doing select by locations and exports since I already created. But you could do a select by location and export. And if you don't know what those are, go to the video and figure out how to do it because at some point in time you'll need to know how to do it. And you already did it for the midterm, right? Didn't you do how many counties intersected with the little ellipse? How many are entirely within the little ellipse? 2 different questions, huh? How many went and counted them? Good answer. Good answer. Oh my God, that's all right. At least you knew that because there were 2. One was like 17 and one was 11 or something like that. And so it's good, it's good. You made a good choice there. All right. So when we start looking at these questions here, number of deer vehicle collisions per 100 square miles. Does this ring a bell from the midterm exam? Yeah, we did this before. Swine lagoons per 100,000 population or per square. It was per square mile, right? One of them was about 1 swine lagoon for every square mile. One of them was about 0.1 swine lagoons. And one of them was 0 swine lagoons because you had 0 in Forsyth County. So if you have 0, what's the density going to be? 0. And so some of these are intuitive. And for this, I just want to get us a little practice, doing some calculations, but we'll just do the one for Rockingham County. We have 370 deer vehicle collisions, right? What's the area of Rockingham County? The area of Rockingham County. All right, let me go to counties. Okay, right mouse click counties. Let me go down to Rockingham County right here. And I think I go all the way to the right, and there should be a field that says square miles. 572.57. So I'm just going to do 370. 572.7. And what is that equal to? 0.6, something like that? Alexa can't do math for me. Alexa does my math for me.
64.62.
0.6462? Okay. Okay, so it's like 0.6462. All right, so for every square mile, there's about 0.6462 deer vehicle collisions. For every 10 square miles, there's about 6.4. For every 100 square miles, there's about 64 deer vehicle collisions in this study here. And I think after this class, I finish with this class, we're going to kind of I'm probably going to graduate this data set since it's relatively old. Okay, so we did it for Rockingham. I'll let you all go do that for Caswell County. The next thing we're going to do is we're gonna run for Rockingham County, we're gonna run nearest neighbor analysis. I'll let you do the rest for Caswell County next time because I want to do the quadrant analysis. But for Rockingham County, for this set of points here, we're going to see which one is most clustered because obviously when I right mouse click and look at, deer vehicle collisions, there's only 115 here. There's 370 here. So there's more than 3 times as many red dots as opposed to blue dots, but I want to see which one is most clustered. Why, I don't know. That's just part of the exercise. I probably need to think of something a little more applicable. And maybe when we look at different types of crimes or whatever, and maybe moving forward, I'll probably look more onto that. But so what we're going to do here is with Rockingham County with this red set of points, I'm going to click on geoprocessing, or I'm going to click on analysis and tools. Either way, I'm going to get this set of tools up over here. Okay. So I'm going to go to tools and you're going to see something docked in the right here. I've been using ArcGIS Pro for about 4 or 5 years and I'm still getting used to it, but I'm going to click on toolboxes. And once again, we got tons and tons of these toolboxes. And I'm going to go down to spatial statistics. And I'm going to click on analyzing patterns. Analyzing patterns. Okay. So we got a bunch of different patterns here. To me, it's always kind of a good idea to go and check out, see what some of these other things done because they're always adding new tools to this. They're really getting into like vector space. And so kind of making groups like, hey, I've got these 3 variables. I'm going to map them in 3-dimensional vector space and group them all together. That's basically what AI/ML does. That's what it does when we look at things like remote sensing. It doesn't do anything talented or whatever. Even your AI with your voice generation and words and your generative AI, it just starts to, hey, these words look like these words, so we think you're asking this type of question here. But it doesn't do it in geographic space. It does it in some other type of, vector space that gets a little bit out of my skill set. So we're going to look at average nearest neighbor right here. I'm going to double click on this. To me, this is fairly simple to do. We're going to click on this little tool. Come on, computer. Look what we have here. This looks a little different than interpolation. What's it need? It needs an input set. So what I say we were going to do, we're going to do Rockingham deer vehicle collisions. Now what you're going to do for Michael's question is, you just consider Rockingham, you're going to click on call boxes and it's going to give you a report. And what I want to do, distance, Euclidean or Manhattan, I'll click Euclidean. And I'm going to click generate area or generate report. And then if you really want to, you can click on this little button here. Do these things ring a bell? Look what it gives you. It just gives you the results here when you run it. It's pretty straightforward. And if you really wanted to, it says, how does it work? So this learns, okay, who wants to look at math formulas? Not me. Okay, I want to be able to interpret and explain the results. Okay, that's important. So I don't want to foo-foo all of the math behind it because it's extremely sound, but I want to interpret these results. All right, so geoprocessing. All right, let me run this thing. And all it's going to do for all 370 points, just calculate the distance between each point and its nearest neighbor. I'm going to click on view details. Look at, what do I have here? I have nearest neighbor is 0.6371, z-score 0, expected mean distance is this, the observed distance is this, So if the expected distance is much, much higher than the observed distance, what do you think is going to happen? That means that it's extremely clustered. Well, just for the heck of it, let's open it up. Now, what's it say here? When I measured it, it was 2,088 feet. The expected mean distance using that formula was 3,276. It's a lot less. It creates this little ratio that converts it to a z-score. Did we see any z-scores like this in the midterm? No. What does that mean? It's really, really far on the other side of the mean, or to the left or the right of the mean. So what's that mean? Let's just read it. Given the z-score of negative 13.34, there is less than a 1% likelihood that this clustered pattern could be the result of random chance. That's all it means. So what's that mean? If I were to throw 370 points up here into Rockingham County, there's very, very little chance they're going to look like this. Very little chance, like 0.0001. Now that thing didn't want to say like, hey, this isn't going to happen. So they just said less than 1%. Or sometimes they'll use a little swirly equal to sign, approximately equal to 1%. So typically in statistics, we don't use the word zero. We just say less than 1, meaning, all right, it's pretty likely that this stuff is, these points here are clustered. And so what I ask for is, well, I asked you to go do it for Caswell, compare Caswell. Hey, which one is more clustered, Rockingham or Caswell? Because I can't compute densities because obviously this thing has more points than another thing. And we can do the same thing like for crimes. What's more clustered? Armed robbery versus prostitution versus homicides, because we have different numbers of crimes for each of those throughout the city. So it's really unfair to calculate, densities, but this thing can kind of, this thing's like z-score. Z-score, what are the units for z-score? No units. Same thing with this. We result in a p-value for every single data set. Now that p-value represents these 370 points right here. Okay, so this point doesn't get a p-value, this point doesn't get a p-value, this point doesn't get one. Now, when we start running cluster analysis, hotspot analysis, each of these points and polygons will get their own little z-score and p-value and colored in yellow and pink and blue. Because those are what we call local statistics. So those are one of the things that I like. Now, for Michael's, what we're going to do is you're going to right mouse click, zoom to layer, and we're going to do the same exact thing for this. This is like the last question that I added on the end. But to get there, because when you open it up, you'll see data sitting in all different places here. But you're going to run it up. You're going to do that. And I'm going to ask you to kind of, for the last question, is kind of go and do that. And write it like a short little paragraph about how do you interpret the results? What did you expect? Just kind of summon these things up. And I think some people with, safety or criminal justice background would really kind of like this. Like, hey, we need to make some recommendations to NCCU, to do this. Hey, I created a set of points here where they are uniformly distributed. Hey, if I put a point over here near the School of Education building, and it would move the p-value from, lower the p-value to make it more uniform or more dispersed than it does. And so those are some of the things that I would like to see, some kind of thought above and beyond just giving me the answer that I want to hear, and really thinking proactively about some of the things we can do here. All right, now, last thing, how about we don't even bother to do number 3? So what I'm going to have you do is you do number 2 for Caswell County, you number 1 for Caswell County, you do number 2 for Caswell County. And then what we're going to do is we're going to spend the rest of class here running quadrant analysis for Caswell County. And so let's zoom to Caswell County, zoom to layer. And let's forget about this stuff right here. And so what we're going to do here is And look what I already did. I actually went and created like fish nets and good fish nets and bad fish nets and all this other stuff right here. And I created these for a reason, probably I was in a hurry or something like that. But one of the things about this is we don't want to use block groups. And I did put the block groups right there because these block groups mean they're all different sizes and shapes and, they have their own biases and all that other good stuff. So the one thing that I'm going to do is I want to create a fish net of Caswell County. And do I have an outline of Caswell County? Oh, yeah, I even have an outline of Caswell County too. Wow, look at that. And so we start to ask some of the big questions here. And I have the fish nets right here that I created. I created some good fish nets and some bad fish nets. But I want to kind of walk through the process here where that I'm going to make a fish net. Does anyone understand what I mean by fish net? It's just a grid. A grid, sometimes we hear the word lattice. Okay, Lattice. Now, first thing I want to do is, well, how big is each side going to be? I got my formula right here. So I've got the square root of 2 times, well, what's the area of Caswell County? Can you calculate the area? No, we don't need to. Guess what? Somebody gave it to us. So I can go down to the bottom right here, 428.44. How many points are in Caswell County? How many points are there? 1, 2, how many? 115. What are the units for Caswell County? What's the unit for square miles? I just said it. Miles squared. And let me point this to everyone right here. Okay, miles squared. Now, can we do this calculation? Two times 428.44 divided by 115. Turn that component side into the square root thing. I get 2.7296. Did anyone get that? We're just waiting for me. So the answer is 2.7296, and that's equal to how many feet? By this by 5280. 14,413 feet. Why do I care about the feet? When I create the fish net, the units for state plane are in feet, so feet from a 0 point. So if I'm going to start kind of filling in some of these things here, because we kind of talk about this process here where I say, all right, how many points are in the county? 115. So I'll just put 115. What's the size of the county? 428.44. What's the quadrant side? 2.7296.
And I'm sorry, how did you calculate that one?
I did 2 times 428.44 divided by 115, and then took the square root of all that stuff.
Okay.
Yes. $52.80. So the number of feet in miles. Number of feet. So I multiply this times 5,280. And then I just kind of multiplied 2 times 428.44 divided by 115. Took the square root of that. Took the square root of that whole thing. So I developed a study area which has 37 quadrants and 77 sightings within these 37 quadrants. Ooh. All right. Looks like I already went through and did the answer here. So I want to figure out what I did there. All right. Couple ways I can do this here, but let's see what I did there. All right, so one of the other tools, and this is kind of what I want us to get into, is I want to be able to create a fishnet for this county. So I'm going to go to Tools. Now, do you think I know where to find fishnet? I might. You think you all do? No? So you know what I'm going to do here? Under Tools, I'm going to type in the word fishnet. And look what comes up. Create fishnet. So I'm going to create a fishnet. All right, I got some input parameters. Well, I'm going to call this fishnet for class. So I know this is the right one. What's the cell size width? 14, 413, 14, 413. And I want to create polygons. All right, there we go. So under the template extent, I want to focus on Caswell County. And so now, when I put on Caswell County, what does it get popular? What are those big, gigantic, ugly numbers? Latitude or northing and easting in feet. I didn't do any of this stuff. So feet. And so my width, 14,413, 14,413. I don't want to create label points. I want to make this a polygon. Because if I store it as lines, can I do a spatial join? I have a spatial join on it. Why? Because, well, it's got to count stuff within. Fishnet for class. Here we go. Now you notice this number is going to come up a little bit different. Oh, okay. This is something totally different. Okay. Okay. This is something totally different. But so we're going to go back to number 5 here because this is, we're going to go back to number 5 with the quadrant analysis. So we're going to create we're working on number 6 right now. So we're going to create a quadrant analysis and Poisson distribution. Okay. So next, what's going to be my study area? I'm going to run for spatial joins, right? I'm going to count the number of points within. Some of these have zeros. I see a 0 right here, right? I see a 0. I see a 4. I see 6. I see a 1. I see another 0. Because all we're gonna do is map that frequency versus a Poisson distribution. Now, the big question is, when I run the spatial join, should this polygon be part of my spatial join? Who says yes? Who says no? Why? Who says yes? We got some yeses. Who says no? Who's waiting for me to answer? Everyone's trust. Me, I wouldn't. Why? Because do I have points for over here? No. So when I run spatial join, this one's saying like, hey, you're counting the whole here, but this whole area doesn't have points. Now, ways that I can circumvent it, hey, let me go get the whole points for the entire study area. I could do that. Or I could just say, hey, let me run a select by location for every single quadrant entirely within Caswell County. Can you do that? Can you find every quadrant within Caswell County? Have you done that on an exam before? Yes, you did. This stuff kind of builds on each other, right? Like finding the little number of counties entirely within the ellipse. Same exact idea. So this one, do we want to count this one? No, 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 maybe, maybe, no, 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 yes, 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 yes. Why? And this is where we get into bias. You know, because a lot of times when you see people, if I were to run quadrant analysis on just this whole area, you're going to see a lot of 0, 0, 0, 0, 0. And what do you think people are going to say when they run that? Wow, that's pretty interesting that the areas around Caswell County, the border, have 0 or 1 sightings. And why do they have 0 or 1 sightings? Because only a small portion of them go into Caswell County because we're only working with Caswell County. So we can circumvent it one of two ways. One is we can bring in all the data points and do that, but now we're working with deer vehicle points outside of Caswell County. Okay, or we can just include the quadrants that are entirely within Caswell County, which there might only be 30 or 40 of them, but I'm gonna make this really simple exercise. So we'll just include 30 or 40 of them. It's not gonna break my heart. Yeah, and for this simplicity, okay, is there a way that we can pick every single quadrant that occurs within Caswell County? You bet. And we're going to just work with that and run the spatial join from that and the quadrant analysis from that. Okay. And we will be done. So map, select by location. What do I want to pick? I want to pick the fish nets. That are completely within what? Caswell County. Look what I got there. That's all I want to do. Now I could run the spatial join and then get rid of them later, or I could get rid of them now and run the spatial join later. It doesn't matter. I could have included other points. It's also going to get a little bit goofy up on that north where we'd have no points because we don't have we don't have deer vehicle collisions for state of Virginia. So now there's 37. Ooh. You notice question number 5 has 37 in there? That's pretty cool. I don't think that's an accident, I guess, right? I don't know. Maybe I really have done this already. Okay. So how do I just export out these quadrants to work with and get rid of everything else? How do I export the data? Exactly. Right mouse click, data, export features, and I'm going to call this working quadrants. Oops. So now, if someone asks you, hey, why are you only working with those? What are you gonna say? Someone says, why are you only working with those? That's not all of Caswell County. What do you say? Exactly, all the quadrants entirely within Caswell County, because we're gonna have, you know, I think they sometimes use the word spatial bias, spatial bias. You know, and a lot of times if you see edge areas that have like 0 values or low values, you know that people treated it as an island. Treat it as an island, like, hey, we're just working with Caswell County instead of doing something like this. Now we're going to run a spatial join. Spatial join, I want to count how many times each one appears. All right. So this quadrant, I'm going to get 2, 2, 1, 5, 2, 0, 1. How do you all do that? How do you do that? Did we already do this before? Week 1? Those of you who never learned GIS before, I'm having you do spatial joins. It's easy. Okay. So now with my working quadrants, I'm going to right mouse click, joins and relates, add a spatial join. What am I going to join it to? Does it matter which deer vehicle collision I join it to? Does it matter? No. Why? Well, there's nothing here, so I can do it for the whole data set. Well, I'll just do it for the Caswell one. Is it going to count any of these? No, because there's nothing there to spatially, for it to be spatially joined with. So working quadrants, keep all. Let's see what we get here. What do I get? I got 37 quadrants. They go from 9 . This is weird. Why does this join count? Oh, I knew that. Yeah. Sorry. That's weird. Okay. So, all right. Glad I got Philip there. Then. All right. I noticed it was wrong. All right. So I want to join working quadrants to what? That one. Yeah, I accidentally clicked them. Sorry. There we go. All right, so now I got my join count that goes from 8, and I got a whole bunch of zeros, right? Yeah, what's up? You see me? Say no. All right, thank you. All right, so now we got this, and if I wanted to, I can make my nice pretty maps right here with my symbology. We're gonna move forward and we're gonna move forward with the join count right here. And so when we look at it, look what we got here. We have 0 to 1, 7 to 2. This. Now, what are the units for these? Do we have to normalize by area? No, why not? They're all the same area. So I can just say 8, 7, 6, 5, doesn't matter. So that's the power, or the, because deer vehicle collisions, they don't care about what township or block group you're in. So there'll be certain phenomena where you can create these quadrants. Now, if I were to do it for crimes, yeah, I could do it for crimes, but you need to understand certain quadrants have more people with the higher potential for crime. So you're going to have to, how do you calculate how many people live in that square? It's hard. You got to like prorate the areas and do all this stuff that I'm sure is going to be difficult. Okay. So now, how does this compare to a random distribution? Now, the last, I don't want to use the word trick, but you can see here, I didn't realize that I had kind of already done this already. And what we can do is just cut and paste this stuff straight into Excel at some point in time. Because it looks like I've already done it, and we're going to cut and paste it into Excel as well. But to get a count and a frequency for this, all we're going to do here is we're going to run a nice little summarize. What does summarize do? Count the number of times something appears. So how many times does 8 appear, 7 appear, 6 appear, 5 appear, 4 appear, and then we're going to compare that to a Poisson distribution. So I'm going to do working quadrant statistics while we're here. I don't even know what join count. Count. So now when I get this table here, did I just create this or did I create? Oh, no, not this one. Does this ring a bell? In this assignment here? I got right there. Now, what I want to do is I want to calculate this stuff because I gave it to you already, but I want to go through it and calculate this stuff. And I want to create just a nice, pretty frequency graph for an expected distribution, what it would look like. So basically, we're going to copy this table, or we'll probably, if you want, we got time to fill in this table from scratch. All right, so when I go back, exercise number 5, I've got a quadrant analysis example right here. So this is in the folder that I've got right here. What I got here, this is it. This is the answer right here. Now, how do we create this? Look at all this big fancy stuff that we've got. Oh my gosh. So I want to create another sheet because in case you want to do this or have to do this at some point in time, I want to calculate this myself. Is there a way that I can cut and paste this thing straight into Excel? You bet. I'm going to do something called switch and copy. Hello, Excel, here you are. All right. Delete. Delete. So what do I have here? This join count is X. Frequency, is there another better word for frequency? Well, I think frequency describes it pretty well. And then, so we got our count. So basically our count. Okay, so all this says is that 6 of them have 0, 11 of them have 1, 8 have 2, 6 have 3, so forth and so on. All I'm going to do is compare this to what a random distribution would look like. And in this case, this random distribution is what we call a Poisson distribution. Poisson distribution. So I'm just going to graph this versus a Poisson distribution. And I'm just looking at the other Excel thing right here. So what's the Poisson distribution equal to? All right, we have I'm going to Control C. Poisson distribution equals POI, guess what I got here? A Poisson distribution. All right, I got an X, a mean, and a cumulative. What's the X? What's the value? Count, right? Now, the mean is the average number of sightings per quadrant. How do you calculate the average number of sightings per quadrant? There's 37 quadrants. How many sightings are within those 37 quadrants? Could you count those? How? You want to go count them? You want to do select by location? We could do it even easier. Guess what? How? Someone's thinking, exactly. If I really wanted to. Statistics. Oh, it's not even. Right mouse click. Statistics. Where's my properties? 77. All right, did everyone see what I did there? There's 77 dots within these quadrants. How do I know? Well, you could go and run a select by location. I dare you all to. You'll take a little extra minute or two. Or what happened? When I ran the spatial join on just the ones that have a polygon around it exactly, Will, is that I ran this one right here. Here's all 37. All I did was just, if I really want to watch statistics, not only 77, but .1. What do you think 77 divided by 37 is? 2.0. It's actually like 2.08 something, something, something. Okay, so when you go to that Excel spreadsheet, you see that 2.08, that's where I get it from. So now what can I do is Poisson distribution, our mean, 2.1, cumulative, I'm going to type in the word false for now. All right, Juan, do you have a question?
Are, have you checked all of the accounts? I know in your video you mentioned that it's important to add the 7 one.
Yes, the 7 one. One thing that I did do, watch. Do you see a count of 7? Insert. So what's the 7 going to be? 0.
0.
Yeah. 7's going to be 0. So now, in a normal Poisson distribution, random distribution with an average of 2.1, there's a 12.2% chance that it has 0, a 25% chance that it has 1, a 27% chance that it has 2, an 18% chance that it has 3. If I added up all those chances, what do you think they're going to add up to? They better add up to 100 or 1. Six. If I really wanted to, let me put a 9 and a 0, there we go. Just for the heck of it, let's put a 10, put a 0 and a 0. Okay. Yeah, right there. So these are the chances we have falling within it. Now we have a frequency right there. What is our expected frequency? Because I could go and calculate 6 divided by 37, 11 divided by 37, 8 divided by 37. What's the significance of 37? The number of quadrants that we have within it. It's got to be one of those possible values. How do I calculate the probability? Expected frequency. What's it going to be? Just equals this little Poisson distribution times 37. Now, what's the one problem with this column that you see? What's that? They're not rounded. Why does it have to be rounded? Because the frequency. You can't have 4.53 quadrants, right? But watch, when you add them all up, look at that's 37. So how do we round in Excel? Just type in the word round, watch, round, whatever you want to round. How many digits do we want to round to? 0, exactly. 0 decimal points. So now look what we got. It adds up to 39. I don't like that too much, but 37, 39, because it's rounding up. And just for the heck of it, instead of 2.1, we did 2.08. And let me drag it down. So you might get something slightly different. You got 38. If I rounded down to from 2.1, which it gave us, which it gave it to us in the other one versus 2.1. Now look what we got here. So now we got a frequency of 6. We expected 5. 11 expected 10. 8 expected 10. 6 expected 7. Can you graph these things next to each other? Yeah. Just make a nice little, I gotta remember my Excel. But, pick out the 2 columns and just graph these next to each other. We can forget about the conglomerate Smirnoff test for now, but we graph these next to each other. So, what can I do here? Highlight this column. And you notice I have all this stuff sitting right here. I got it all kind of sitting here with the 39 and, the 2.08. Look at that big long number that I cut and pasted in. I was pretty serious that day when I created it. But so now I can grab this, I can grab this, and I'm just grabbing the frequencies, and I can go back and change it later. Change the headings later, but insert. I always get really bad at these 2D lines. Boom. Look at that. That's pretty cool. Does everyone know how to change charts in Excel? Please nod your head. I'm not a super great at Excel, but we can, you got to click on the data there, right? So you can do fill, border, select data. So on my x-axis, I can select this count right here. Boom. So now okay, there. For now you can see the 0. So instead of it starting at 1, it starts at 0. I can call this, instead of series 1, series 2, I can say frequency expected. There we go. Ready to go. Cut and paste this thing into Excel, into a paper, into a whatever. And so what does this tell you? It was in our last couple minutes. What does this thing tell you? If someone said, we've spent the last 30 minutes making this chart, using some GIS magic, running some spatial joins, using all skills that we've already done, but we're starting to put them together. And that's where you kind of turn from a GIS user into a real life problem solver. This is what we call loosely coupled applications, where we're bringing them from one application into another. What's it tell you? What these two things are near each other. What's it mean? Can you tell me kind of in one sentence, what's this mean to you? What's that? It's not random. Oh, it is random. I'm sorry, it is random. Yeah, because this orange is an assumed random distribution. So these near vehicle collisions, what are they? Random. They match up really closely with a random distribution for these points. Now, would we see a nearest neighbor analysis for Rockingham County? We saw the exact opposite, right? So there's different ways that we can measure this randomness. So nearest neighbor analysis to me is very coarse, right? It's just it's really simple to calculate. ADU, run through an average this, where this thing is a little bit different. What if you were to select a different set of points? You think you get a slightly different pattern? Probably. It's gonna be biased or better or worse? Probably not. So I like doing things like this. I like it because I got a paper out of, paper out of it that you have to read and things like that. But, for your paper, for your position paper, I want to look at the spatial distribution of gun crimes in Durham. Run a quadrant analysis on it. Create a little quadrant analysis on it. Okay? And do it. Now we go through something obvious like swine lagoons, because we all know where the swine lagoons are, right? But hey, we had a student who went and did farmers markets versus convenience stores versus grocery stores, and farmers markets look like this, while the grocery stores look like this. That didn't match up with this, and the convenience stores didn't match up. So hey, using my my Ripley's K, which I didn't talk too much about, and my nearest neighbor analysis, and my quadrant analysis, I can say that farmers markets were a lot more random than the other two, based on some of the available metrics. Not all three, but some of these. To me, this is very close to random. All right, because you're going to go with, I think we already kind of did this, but, go and practice with some of this. But I wanted to get through this. So for the rest of the exercise, basically, what I want you to do is kind of fill in the needs based on what we did previously. Because for the exam, I'm going to kind of give you a quadrant analysis. And some of these are going to make sense. Hey, all these probabilities better add up to 1 or very, very, very close to 1. Because you might have like really, really tiny numbers, like down to 50 that add up to 1. And like the expected frequency should be rounded, because we can't have like 4.2 quadrants, either 4 or 5. So exists some granularity with these data. And so make sure we have these, because at the end of the day, we're just graphing this. And then we also ran the nearest neighbor analysis, which is, it's simple. But these are inferential statistics, meaning this is random. This is what we see. Are they different? Yes or no? And we can run some statistical testing, with the Smirnoff test to do that. But for now, we could just kind of eyeball it. Okay. All right, so we got that homework due, and then we'll have the other one due in 2 weeks. They should be up in Canvas, and I think I'm done. Anyone else want me to talk anymore? I want to get home and I want to catch the Mets. So. Well, I'll see you all later.
Thank you.
All right, see you later.
Thank you. Bye-bye.
All right, see you.